In our practice video, we reviewed centripetal forces, and in that particular example, we were looking at the force of gravity being the centripetal force that keeps the moon in orbit about the Earth. But other forces can be centripetal forces. It's not just the force of gravity. Tension forces, normal forces, weight forces can be centripetal forces. And so we're going to look at an example now of a tension force being a centripetal force. Let's consider a ball at the end of a string being swung around in a vertical circle. Now, if we do that, the string is not going to be horizontal circle. The string is not going to be horizontal. The object is going to cause the string to pull down at an angle. So the tension in this case can actually be thought of as two different forces. We can break it up into its horizontal and vertical components. There's the tension horizontal, and there's the tension vertical. These are the preferred set of components that we've talked about before. Now, the tension in the horizontal direction points in towards the center of the circle, and the tension vertical points up, and it balances the other force which is acting on the ball here, which is the weight force. So what, if any of these, are centripetal forces? Well, the horizontal tension force is the centripetal force. This is related to the example in your textbook, Chapter 5, the example box 5.1. And if you haven't already worked through that example as a part of your reading for this day's lecture, you should pause the video now and go do that. Now we want to look at what happens if we take this ball and we whirl it in a circle that is vertical, so up and down. Well, here we also have a tension force and a weight force. Both of these forces are centripetal forces. Now, the tension force is the only one that points towards the center of the circular path here, but the weight force is also pointing along the radial direction, along the line that goes to the center. So it's also a centripetal force. But one of these is positive and one of these is negative. If we assume that the mass of our ball is 0.5 kilograms, the radius of the circular path is 0.3 meters, and the velocity is 4 meters per second, then we can apply Newton's second law to centripetal forces for this object. And here we would have the tension force is positive, the weight force is negative, and that equals mass times centripetal acceleration, which is v squared over r. Now, the reason tension is positive is because it points towards the center of the circle. Weight is negative because it points away from the center of the circle. So let's solve for the tension force. Tension then equals weight plus m times v squared over r. And you should pause the video here and do the math and see what answer you get and compare it to the answer that comes next, which is 31.6 newtons. So in this case, the tension in the string is 31.6 newtons. Now let's consider a different example. Let's say that the ball, instead of being at the bottom of the swing, is now here halfway on its way up to the top. Well, let's look at the forces that pull on the string. I have my tension force, which still pulls towards the center of the circle, and the weight force always acts downward. Now, if you look at this, the weight force no longer points along the line that runs to the center of the circle. So it is no longer a centripetal force. This means when we write out Newton's second law, we find that the tension force equals m times v squared over r. Put in the numbers and get out an answer. Tension is now 26.7 newtons. Now let's look at the ball when it's at the top of its path. We still have our tension force that points into the center of the circle. And weight, which always points downward, now also points into the center of the circle. It is a centripetal force again. But unlike the first example we did, where the ball was at the bottom of its swing, this weight force is actually positive because it points towards the center. So let's apply Newton's second law of motion. Tension plus weight equals mv squared over r, and solve for t. And we get that the tension here is 21.8 newtons. So in this example, we see that the tension force is always a centripetal force. The weight force is a centripetal force at the bottom of the swing, where it's negative, at the top of the swing, where it's positive, and that the value of the tension force varies if the ball is rotated in a circle at a constant velocity of 4 meters per second. Now let's consider a slightly different example. Let's look at a car going around a circular curve, and we see the car here represented by the box, and it has a velocity which points tangential to the circle. Now this is question Q9 out of chapter 5. And it asks what force keeps the car going around this circular path, keeps it from slipping off the road basically. And the answer to that question is a static friction force. Static friction is what keeps the tires from slipping on the road's surface. So static friction is the centripetal force. Now static friction forces can have a value that is greater than or equal to 0, but is always less than the normal force on the object. So let's look at the car in the vertical direction. The two forces that act on the car would be the normal force of the road up on the car and the weight force pulling down on the car. If we apply Newton's second law of motion here, we see that the normal force has the same magnitude as the weight force, and that is mg. So that means our coefficient of static friction has to be somewhere between 0 and the value of the normal force. For rubber tires on an asphalt road, the average or standard, most common value of the static friction force is 0.8 or 80% of the normal force. So let's assume that the static friction force here is 0.8 times the normal force. If I apply Newton's second law of motion centripetally, I get then that the centripetal force equals the mass of the car times the speed squared over the radius of the circle. Or 0.8 times mg equals mv squared over r. Now if you look, you'll notice that there's mass on both sides of this equation. So if I divide through by mass, the mass basically cancels out. And I'm left with 0.8 times g equals speed squared over r. Or speed squared equals r times 0.8 g. So here's what we had on our previous page. Let's solve for the velocity. See what speed this car can have going around this curve. So if you look at our formula for velocity, velocity equals the square root of radius times 0.8 times g. You'll see that there's no mass in this equation anywhere. What this means is that the maximum safe speed a car can have, or any vehicle for that matter, can have going around a curve does not depend on the mass of the vehicle. And this shouldn't be too surprising. If you have ever, for example, gotten off the interstate on an off-ramp that is circular, you've noticed that there's generally a sign there that says 35 miles per hour on that circular off-ramp. It doesn't say 35 miles an hour for a Cooper Mini, 30 miles per hour for a Chevy Suburban, and 25 miles an hour for a semi-truck. It doesn't have different speeds for different vehicles. There's only one sign. And that's because the maximum safe speed doesn't depend on the mass of the vehicle. It depends on the radius of the curve. So if we assume that this circle has a radius of 105 meters, let's see what the maximum speed would be for any vehicle going around this curve. And we find that the maximum safe speed is 28.7 meters per second. Next, we're going to move on to Chapter 6 and start talking about work. Work is defined as moving something. For example, I can push on a wall and I can push on a wall even more. And I can push and push and push on that wall until I am plumb worn out. But if the wall doesn't move, then I have done no work on the wall. So mathematically speaking, work, for which we use the symbol capital W, weight is lowercase w, is equal to the force you apply times the distance through which the object moves because of that force. Now there's something very important about the direction of the force and the distance moved, or the direction the object travels. Those two things have to be parallel. Now let's consider a person pushing a box with a horizontal force of 7 newtons. And let's assume that the box moves a distance of 8 meters in the direction of that 7 Newton force. Well, the work equals the force times the distance, or 56 Newton meters. Now, the Newton meter is the unit of work, but much like we have done with other multi-units in the past, we give this a new name. We call this the joule, or capital J. And joule is the unit of work. Now let's see what happens if there is a kinetic friction force that acts opposite the direction the box is moving. We have work equals negative the kinetic friction force times the distance moved. The reason that the force is negative is because both force and displacement are vector quantities, and the force in this case points opposite the direction of the displacement. So when we put in our numbers, we get a value of negative 56 joules. Now the value of work done by the person pushing was positive. The value of the work done by the frictional force was negative. The positive and the negative signs for our work are important. They tell us something very important, and we will get to that a little later. It does not, however, tell us direction, because while force and displacement are both vector quantities, work is not a vector. Work has only size, but no direction associated with it. So that means the positive or the negative value of work are not telling us something about direction or which way. We've already looked at the work done by the person applying a force. And the work done by the kinetic friction force. Now let's consider the other two forces that are acting on this box. There is a normal force and a weight force. And let's assume that the box still moves a distance of 8 meters. Well, the box moves horizontally, but the normal force and the weight force both point in the vertical direction. So the box is not moving along either the line of the normal force or the line of the weight force. It doesn't move in either of those directions. Therefore, the work done by the normal force and the work done by the weight force in this example are equal to 0 because the box doesn't move in those directions.